Oh, welcome to one of my favorite topics in math. This is something I absolutely still remember and adore from when I was in algebra. I know that doesn't make you guys feel excited by it, but that's okay because I am excited. I love this. Just the elegance of how this works is going to be fantastic. And what is this? What am I talking about today? That would be solving linear systems. What, Mr. Brayman, are you talking? Oh, I forgot my pen. Okay, there we go. What are you talking about, Mr. Brayman, when you say, what does solving linear systems mean? Great question. That's why it's right at the top here. What we're trying to do is find out how two lines interact in the same plane. How two lines, or in this case, we're going to do two lines. You can do more than that, but how lines in the same plane interact. And you're saying, okay, well, how do two lines in the same plane interact, Mr. Brayman? Well, I think that's a really fair question. And to that question, I would say there are three different ways. We could have line A and line B. Ooh, right there. I like that. I like that. And they interact in this way. They intersect at one point. They intersect at one point. So we have intersect at one point. And the next one, it says, well, how else could I do this? Let's think here. How else could I draw two lines and have something different happen than interact or then intersect? Oh, how about, I'm going to do the best I can because you know how terrible I am at lines, and that's okay. I've been practicing, still not great. These lines should be parallel lines. These are parallel lines. That's a little symbol used for parallel lines. And how many times did they touch? None times. Very good. So zero interactions or zero solutions. All right, and this would be one solution over here. So one solution. Mr. Brayman, what's the third way? What's the third way? Well, I'll show you right here. This is a line that I have. I've got this line right here, mostly a line, and that's okay. Also, hey, me being, kind of iffy at drawing lines, that's going to come into play in a second too. So if I draw that line, what's another way it could be? How about if it is the same line? Oh, that's pretty bad. Hold on, oh no. Okay, I'm just going to try to do it like this. That doesn't look good either. Okay. Let's kind of make this a little, oh, you know what? I'll just make it thicker. How about that? I'll do this. And we're going to call this the same line. And if it's the same line, it is an infinite number of solutions. Infinite number of solutions. Interesting, interesting. So we got all this business going on. Oh, that's a little too much. Here we go. Let me take that down a little bit. There we go. Infinite number of solutions. Is this right? That looks pretty good. So what are three common ways that we're going to use to solve systems of linear equations? In other words, where do two lines interact? How do they interact? Do they cross? And if they cross, where do they cross? So what are the three example number one, because that's right there. Way number one, graph them. Graph and see where they interact. See how they interact. Okay, what would the second way be? Well, we have these things called elimination methods. What are elimination methods? Good question. I'm glad you asked that. We're going to eliminate something, and that thing we're going to eliminate is a variable. So we'll get that, see what that looks like here. The third way will be substitution. And without a doubt, this is one of my, if not my most absolute favorite things to do. Substitution. Oh, it's so nice. So nice. It's just so elegant. So what we're going to do is take 2 examples. I'm going to do 4 examples. I'm going to break this up into part 1 and part 2. We're going to take 4 examples and we're going to do all 3 ways for them. Okay, and then we're going to talk about at the end, we're going to talk about what are some of the benefits and what are some of the drawbacks to each of the methods that we use. So example 1 says solve the linear system. This is how linear systems are usually written. It's got this little fancy bracket, and then it says you got the 2 lines here. It says y equals negative 2x plus 6 and y equals x plus 3. Method 1, solve by graphing. So you can, however you want to graph these things. I see that these are already in slope-intercept form. So if they're already in slope-intercept form, plot the y-intercept, and then use the slope to find different points. You could do table method, where you find some x's and y's, where you plug in some x's and y's, plug in an x, find out what y is. You got to get 2 points on there, but you can do that. You do a table method. You could do read the form. Not that they're always going to give it to you in a form, but you could change it to a form, a y equals mx plus b, or a point slope form, or something like that, or maybe even doing, I don't know, intercepts. See, it all comes together. It all comes together. In this way, I'm going to do this one. These are both in slope intercept form. And so in this case, I'm going to say that the m, or my m right here, is negative 2. And my b, my y-intercept is 6. So I'm going to plot my y-intercept at 6. And using my slope, negative 2 is like negative 2 over 1. So I would go down 2, right 1, get another point, down 2, right 1. I can get a bunch of points in here. And this is my first line. And this right here is already the drawback. And I hope you're seeing what this looks like here. Oh, that's bad. Oh, hold on. Let's do this right here. See if I can. Oh, close enough. Close enough. So that's the first line. I think you're seeing what a drawback is, right? You got to be really good at drawing lines. If I had a ruler, it'd be even better, but rulers kind of mess this board up a little bit. The second one, my slope is 1 and my y-intercept is 3. So my y-intercept is 3 and my slope is 1, or 1 over 1. I'd go up 1, right 1, up 1, right 1, up 1, right 1. Okay, get all limbered up here. Let's see if I can do this one a little better. Oh, not even close. Let's try that again. I'm trying to pick my spot here. Close enough. Okay, so I've got my 2 lines, and how this works is these 2 lines cross. We graphed them correctly, which we did, but they cross, and it looks like they go right there. So, and to me, it looks like it's at 1. The solution would be at 1, comma 4. This would be your answer. This would be your solution. Your solution is, oh, hold on, let that catch up to me here. There we go. Your solution is where they cross, if they cross. In this case, it looks like they cross at 1, comma 4. You're only as good in graphing as your drawing ability. You can see why I struggle with the graphing one, right? Also, your accuracy might struggle. Even numbers are going to be okay. Like when we did that slope thing, it was pretty easy to see that because I, touched 2 points together. But what if it was like halfway in between, or 2/3 of the way in between, or 9/74 in between, right? We would have some trouble with that. So graphing has some limitations. Let's take this same example and let's do another method to it. We're going to do the elimination method. And here's the elimination method. It says add or subtract the equations. Yes, we can do that. by the way. Add or subtract the equations to eliminate one variable and then solve for the other variable. You may need to multiply one or both equations to be able to eliminate a variable. It's not the case in this one, but we will do an example that makes that happen here. We've got y equals negative 2x plus 6 and y equals x plus 3. Can I add or subtract these equations? And yes, I do mean subtract an equation and get something good out of here. The answer is yes. Let me rewrite these here. Y equals negative 2x plus 6, y equals x plus 3. Look at y and y. I've drawn them both poorly, but that's okay. But if I did y minus y, what is y minus y? It's 0, Mr. Bremen. Hey, thank you. All right. We have 0 equals, what's negative 2x minus x? Negative 3x. And what's 6 minus 3? Well, that would be plus 3. And hey, I've got an equation with only one variable, and I can solve that. There we go, I'm back. Substitute, oh, then we need to solve for the variable. Solve for the variable. I can solve for x right now. If I subtracted 3 from both sides, I get negative 3x. I'm sorry, negative 3 equals negative 3x. Divide both by negative 3. And, well, negative 3 divided by negative 3 is 1. So x equals 1. Yay! But I'm not there yet. Because in a line, if they were intersect, right, it'd be an x and a y. Do we have anything that says like y equals, or are we able to find y? Oh, hey, look at our original equations. Substitute the value into either original equation to find the value of the eliminated variable. We eliminated or got rid of y. So we need to get y here. Let's take our original equation. We'll do the top one. Why not? Y equals negative 2 times 1 plus 6. Well, negative 2 times 1 is negative 2 plus 6. Y equals 4. Write the solution as an ordered pair. X is 1, y is 4. Where have I seen that before? It's like, I mean, even as bad as I did on the graphing, right? I kind of was able to figure it out. It was 1 comma 4. That's kind of cool. That's kind of cool. That's how you do elimination. Let's take a look at the last method. Let's take a look at the last method. It is called substitute. It's at the bottom of the page, isn't it? I knew you guys are like, Mr. Brayman is right there. Okay. Look, it's the same example. Y equals negative 2x plus 6 and y equals x plus 3. It says solve one of the linear equations for one variable. Well, actually, they're both solved for y. That's kind of nice. We can pick and choose in this one. Then it says substitute the result into the other equation. What does that mean? let me rewrite this. Y equals negative 2x plus 6. Y equals x. Y equals x plus 3. So I'm going to take the second equation. If y equals x plus 3, anywhere I see y in the first equation, instead, I'm going to substitute in x plus 3. What does that look like then? It looks like x plus 3 equals negative 2x plus 6. Oh, that's kind of nice. I know it's on different sides, but hey, I can solve this. What if I added 3x to both sides? I just got ahead of myself. Added 2x to both sides. So this would be 3x plus 3 equals 6. If I'm solving for x, I could subtract 3 from both sides to get 3x equals 3. And this is kind of funny. It's the same problem, right? So if I divide both sides by 3, x equals still equals 1. And we've just solved for the variable that remained. And this says plug the result into equation from step 1 to find the other variable. So in other words, I can plug this into either equation again and find the other variable. I found x first. I now need to find y. I like that second equation. How about this? Y equals x plus 3, or 1 plus 3. And amazingly enough, y equals 4. So I get 1 comma 4 again. That is amazing. And to check if you're right, you can plug them back into the original equations. Does 4 equal 1 plus 3? Yes. Yes. For this first one, does 4 equal negative 2 times 1 plus 6? Well, 4 equals, this is negative 2 plus 6. That is 4. 4 equals 4, and that's true. Fantastic. Oh, I love how that, oh, it's just, oh, substitution. Just makes me so happy. I love how that goes. Okay. Now, when you're going to, again, let me just kind of pause here for a second. When we're taking a test, when we're doing things, what we're going to look for is the most efficient way to get these done. On the test, you're going to have, I think, probably 3 or 4 or 5 questions. And what you're going to do is pick the most efficient way. You're going to have to use every way at least one time to show me you know the different ways, but you'll be able to use your favorite method more than one time. Substitution. It's all right. Here we go. I'm going to do example 2. I've got 3x plus y equals negative 3, and I've got negative 2x plus y equals 7. For graphing, what I would do here, I'm just going to solve. Actually, you know what I'm going to do? Yeah, I'm going to do that. I'm going to solve for y. I'm going to solve for y. If I did that, the first equation would be y equals negative 3x minus 3, because I subtracted 3x from both sides. The second one would be y equals 2x plus 7. And I graph these. First one, y-intercept is negative 3. My slope is negative 3 also. I could go down 3 and right 1. Or I could go up 3 and left 1. That still gives me negative. Up 3, left 1, up 3, left 1. And here we go, because I'm graphing. I can do this. I can do this. Oh, we'll take it. We'll take it. That is acceptable. The second line is 2x plus 7. My y-intercept is 7. My slope is 2, a positive 2. Rise 2, run 1. Or I could go down 2 and left 1, because that's negative divided by negative. That's still a positive. I could go down 2 and left 1. Ooh, interesting. Ooh, down 2, left 1. Okay, here we go. Oh, there we go. There it is. Hey, it does look like they touch. It does look, I think I did okay here. It looks like they touch right here. Better arrow. What is that coordinate point? It looks like it goes to negative 2, comma, positive 3. Okay, okay here. Now, when you're doing graphing, you just do the best you can with it, the best estimate that you can. The elimination method, though, let's rewrite what we've got. I'll start with 3x plus y equals negative 3, and negative 2x plus y equals 7. I see y's again. I could do that subtraction business again, couldn't I? I could do that. What if I subtracted the first one or the second one from the first one? What do I get here? This would be like 3x minus negative 2. Minus a negative is? Yeah, go ahead. Plus a positive, Mr. Brayman. Hey, there you go, plus a positive. So 3x minus negative 2x would be 5x. Y minus y is 0. And negative 3 minus 7 is negative 10. Okay, I've got 5x equals 10. Divide both sides by 5, and x equals 2. Or negative 2. Oh, I'm sorry. This is negative 10. Hold on. I got excited. Let me slow down. Divide by 5. This is negative 2. Look what we got there. Yeah. But if this is, we got to figure out where they're crossing. So it's not just an x value. It's also a y value. Plug this back into one of the other equations. I'm going to take that top one. 3x, or 3 times negative 2, plus y equals negative 3. This is negative 6 plus y equals 3, negative 3. Add 6 to both sides and y equals 3. Oh my goodness. X is negative 2. Y equals 3. This is negative 2, comma 3 as my point. my coordinate pair right there. And hey, got the same thing. Now, we're going to do substitution. And if we get something different, we done screwed up because these two agree with each other right now. Substitution, the first thing you got to do, so we can rewrite these again. 3x plus y equals negative 3, and negative 2x plus y equals 7. So I got to take one of these equations and solve for a variable. I'm going to take, because it doesn't matter what you do. You could solve for any of the variables here. But I'm going to take that first one. I'm going to take that first one and solve for y. So I'm going to get y equals negative 3x minus 3. This is that first equation right here. So now, anywhere I see y in the second equation, I'm going to replace it with that guy right there. I'm going to substitute negative 3x minus 3 in for y. So this is negative 2x plus, and instead of y, I'm going to write, I got negative 3x minus 3 equals 7. Mr. Brayman, why did you put that in parentheses? Great question. You guys are on the ball. I put it on parentheses because if this was like 2y, I'd have to multiply this entire thing by 2. We'll see that at the part 2 video. Okay. So if I do that, I'm just distributing a positive 1 through here. So this is like negative 2x minus 3x minus 3 equals 7. Simplify what you got. This is negative 5x. X minus 3 equals 7. Negative 5x equals 10, because you add 3 to both sides. That looks a lot like this. Divide by negative 5x still equals negative 2. X still equals negative 2. I love it. Then we got to find the y to it, right? So we plug that back in up here, and we get y equals negative 3. Hold on, let's do it like this. Y equals negative 3 times negative 2 minus 3. Well, negative 3 times negative 2 is 6. 6 minus 3 is 3. And once again, we got x is negative 2 and y is 3. Whew. Okay, that's a lot to take in. I get that. This is going to be the end of part 1. What I want you to go and do is go ahead and rewatch part 1. Part 2 is going to be special cases, the times when they're parallel. What does parallel lines look like? What does the same line look like? Okay, so go ahead, rewatch part 1. There won't be practice until I've given the second part out. All right, so with that said, it's okay. We're going to do this one together. We're going to be all right. Hope you guys are having a great evening. Take care. Have a great one.